everybody. My name is Leila de Floriani. I am with the Department of Geographical Science and UMIAX. This is actually my email and contact information. Let me talk to you about the research that we have been doing in my group that I call Geovisualization Group. By the way, myself, I am a computer scientist and actually a mathematician as an origin, and you will see some of the research that I'm discussing about. Our group is affiliated with the Center of Geospatial Information Sciences, which will do long-term collaboration with computer science, and located in the Department of Geographical Sciences, and with the UMIAX and the Department of Computer Science. What are the research areas? Traditionally, my work has been in geometric modeling, in geospatial geometric data structure and algorithms for several applications that went from CAD, CAM, graphics, and so on, and in 3D shape analysis of the group. And our research area, this is still our research area, one of the sort of new topic we have been working on is data analysis, and in particular on topological data analysis. Topological data analysis is a new discipline, if we want to say that, at the crossroad between computer science and mathematics, where the mathematics behind here is a combinatorial topology, and enable us to extract topological information from data and shapes and to do description. And that is basis of one of the big benefits of this kind of approach to data analysis, the robustness for noise and versatility with respect to the type of data that you are considering. And in that area, we are doing application in scientific data visualization. I will say a few words more on that. And traditionally, also this geospatial data processing. Actually, I started my career working on this data, and I went back recently on working on that. By the way, a related graduate course that we're offering here, co-taught with Professor Hanan Samet, is geometric and solid modeling. And not offering this year, but we'll try to offer next year. If you're interested, you'll come and talk to me about that. Okay, this is my group. And I have currently four PhD students, visiting scientists, and when I list the collaborators, these are people on which we co-advise students. We work together every time, and they're all over the world, and actually they have in common of being my previous PhD student of different ages, but all of them we have been working on that over the years. So this is the group that works between UMIAX and the Center of Geospatial Information Sciences. And, And let's say what is really the big current research topic. The first one is, I was talking, is on geospatial data representation, on data modeling and data structures. And the focus here is on big unstructured data like point clouds that are static or can be time varying. Our contribution and work here is on distributed data structure, data structure that can compact, scalable, suitable for cloud computing. So this is the part of the representation that is very important when we want to really work with big data. The analysis part of our work that actually is functional to visualization is what I call topology-based analysis and visualization. When you talk about scientific data visualization, what the process means, I start from data, I need to have a good data management and representation tools, and I need to extract from the data the important information that allow and synthetic information that give ideas to the domain science. In a very simple example that you can see in the slides for a terrain, when I look at the terrain, I'm not interested in single detail, but I'm interested at the peak, the peaks, and the valley, and so on. And the same is, as you could see in the 3D example that I show here. And we are working that by using tools from this combinatorial topology technique called discrete Morse theory. And other thing we are working on combining persistent homology that is unsupervised a learning technique, multi-scale technique, based on looking at the shape of the data at different scales, and how to combine machine learning for some of the projects. Let me talk a bit about a big project that we have been working and the motivation behind that is working with big data, and big data in this case are LiDAR, massive point cloud acquired through LiDAR technology. We are talking even in public domain repository of 1 billion of points easily. So one of the challenges, what people have been doing with this data is and the remote sensing colleagues working on that, they take the data, they transfer to raster grids, and then they operate on that. Our approach here is we work directly on the data, and not only that, but we are ambitious enough to connect them what we call simplicial complexes or meshes like that. So storing the neighboring information of the data about the points. But for doing that, current systems are not able to do that, and not even state-of-the-art data structures. So I've been developing scalable data structure and algorithms for processing and analyzing that. And inside this project, in the analysis, of course, we use topological data analysis techniques I mentioned before. The two major applications we're working on are one on dealing with bathymetric data that are LiDAR data acquired near the coast, between they acquire at the coast and near and in the bathymetry, but up to 20-30 meter deeps. And this is a project with NOAA, the National Oceanic Atmospheric Administration, that we have. The other is on massive scale 3 reconstruction for carbon emission computation from high-resolution LiDAR data. We have a very strong collaboration with the center, with the Reason Campus, Center of Excellence for Remote Sensing, and in particular with the group, the JEDI group. They have been working on LiDAR data for a long time. Now, actually, the JEDI group has been the group who was doing a new mission by NASA that was sent at the end of last year, a new device on the International Space Station, and now they're acquiring data. Everybody is actually very, very excited about that, and a lot of data are coming in, and and on that area we have, and on both areas we have projects, more and more projects going on, because there is a lot of interesting computational problem that arise there, and really big data problem here. When I'm saying application, all these techniques, and I don't want to spend more time on it, this approach that we use for distributed data is sort of application agnostic. And even the same approach we are also applying right now to social network analysis. So, and even the same software. So I'm saying these are the two target applications for that, but it's not only on that. On data visualization, we have been working on visualizing data that are characterized by multiple fields. Let me explain what I mean. Let's the example that you see on the top of the typical example of the hurricane exam, where we represent two fields, temperature and pressure, so that are not a vector data, but are independent fields. How these fields interact together. That is the thing. So I can study each of them separately, or how they interact, and so on. Existing theory are for single fields in the topology, like discrete Morse theory and persistent homology. So actually, we have started facing this problem from a theoretical point of view. I have a couple of PhD students, mathematicians, and we have been working together in developing algorithms for that kind of multi-persistent homology, so when you don't have only one parameter, but you have several parameters. And so our work has been in having new tools for the new segmentation tool and new way for noise removal. One application that we're working on in ocean data analysis and visualization, again with the colleague from the Department of Atmospheric and Oceanography Science here. We have a few other projects that actually use topological data analysis, are very different. One is reconstructing the path of vessel in the sea, in the ocean, from vessel trajectories, road network reconstruction, application also to social network, in particular migration network, with Vanessa Frias-Martinez at the high school, and actually more, let's say, algorithmic and theoretical work towards computation. That's it. Thank you very much for your attention, and this is my very fine.